I guess I should connect this, huh? Okie dokie. So, yes, creature, we all know you're there. He thinks everyone is out to get him, I guess, or something. So, go figure. Alrighty. Ah, thank you. Good morning, everyone. Once again, the smoke has triggered my allergies, so we'll see how this will work today. Alrighty, so we're going back to thermochemistry. We learned a whole bunch of vocabulary yesterday. And today we are going to start talking about calculations using thermochemistry. So there were just like one or two more things that I wanted to talk about first. We just have to kind of define thermal energy, which is going to be like the motion of atoms and molecules. How high thermal energy is fast motion. And conversely, or rather inversely, low thermal energy would be slow motion, right? So the higher or the more thermal energy you have, the faster things are moving. So that's just what thermal energy is definition-wise. So we're going to see that temperature is going to be kind of our way of knowing how fast things are moving. But we also have to consider that heat is not exactly the same thing. And so we'll see what this is going to imply for us later on. So we had a couple of equations yesterday. We remember that like the internal energy was equal to the heat plus the work. Right? So if we are using our energy, we could be giving off heat or doing some work. Or if we are gaining energy, we're either getting heat or we're having work done to us. Right? So we talked about system and surroundings yesterday. And so we were able to talk about these signs as well. So we remember that a negative delta E is going to be exothermic, and a positive delta E was endothermic, right? So we have a few more things to talk about here. We have a special kind of work. And that's going to be that most of the work in chemistry is going to be of this type, and that's called pressure volume work. That's a hyphen, by the way, not a minus. So it's not pressure minus volume. It's pressure volume. And for us, that means that work in this for our chemistry stuff will be the product of the pressure and the change in volume. And remember that delta V is, or delta anything is always final minus initial. And so we can go ahead and do some practice with this. So we know in car engines, right, we have, let's not put a lid on it. This thing is called a piston. And when you have your gasoline blow up inside, that causes this piston to move. And by moving the piston, we're going to be changing the volume of that space in there. So as the piston moves, the volume changes. And the reason for that is, as we're going to find out when we talk about gases, is that higher temperature gases cause a higher pressure. And we know that, or we will find that the pressure will always try and equalize itself with the atmosphere. And so in order to do that, it's going to end up moving this piston. And so if it moves the piston, that's going to change the volume. And for us, that's going to be work. We have done something. We've moved something, right? We know that work was a force moving something. And so for us, that's going to be the product of pressure and the volume change. So we can do a little example of that. So let's say we have a pressure of 1.38 atmospheres. That's a unit of pressure. We have a piston. Let's just say we have a volume of 0.92 liters. Oh my goodness. Increases to 1.41 liters after a chemical reaction. What is the work? Oh my goodness. Done by the system. And just for fun, let's make it in joules. Let's see, 101.3, yeah. Liter times atmosphere is also a unit of energy, and there's a conversion factor for you. So let's go ahead and see what this looks like. So work is negative P delta V for us. And so we just have to understand. So atmospheres is a pressure unit. And of course, we have two other numbers here. So sorry, Star-Lord. Yeah, that's a pressure unit. Other pressure units you might see would be pascals or bars. Those would be kind of other pressure units you might see. But atmosphere will be a pressure unit. And technically, it is defined as it is the pressure that the atmosphere exerts upon an object at sea level. So basically, it's all of the gas atoms on top of someone hitting them at sea level. And that is what 1 atmosphere is. I'll just quickly, let me throw up some pressure units. These are probably the most common pressure units you'll see. But thankfully for us, volume units are easier to identify. because pressure units are kind of strange. But volume units will always be liters or some derivation thereof, or cubic meters, or again some derivation, so like cubic centimeters or milliliters or whatever. Those would all be volume units. Okay, so in this case, we have to identify which one is going to be. So we've seen our pressure, so we know that's our P. Delta V is going to be the change in volume, right? And that's, again, remembering that delta V is the final one minus the initial one. So which one is going to be our final volume here? And which one's the initial one? Yep. So 1.41 liters is going to be our final volume, because if we read the question, it says it increases to that. So that's going to be the final one. And we started at 0.92. So doing this, we can think about our sig figs here. So that's going to be 0.49 liters with that many sig figs. Am I correct? Someone do the math just to be sure. I guess I could do it. I'll be good. 1.41 minus 0.92. Hooray, I did it. Okay. So we'll multiply that guy by 1.38. And so that tells us we have negative 0.6762 liters times atmospheres. That's our unit there. Notice we're going to have 2 sig figs. Yeah, this part is easy. No worries. Since I did ask for it in joules, we have a conversion factor up here that we can use. So, liter atmospheres times 1 liter atmosphere, 101.3 joules. Oh, okay, we have discrepancy here. So Shane versus Kevin. Let's see who's right. 0.6762 times 101.3. And of course I get 68, so it's even worse. So I got negative 68.49. Isn't that awful? So while you got 67 and Kevin got 69, I got 68. So I win, I guess. Rounding this to 2 sig figs would be negative 68 joules. Someone double check that. I can make mistakes too. Though at least all of ours are very close to each other. So again, on a multiple choice type thing, I'm sure you would be able to say, okay, yeah, it's 68, whatever. That's a rounding error or whatever. So cool. So notice, work is negative here, right? So that tells us, in words, that tells us the system has done 68 joules of work to move that piston, to increase the volume. Okay, so that's what that negative sign means. Remember, when you have a negative work or a negative heat, that means the system has done that thing. And so we could also say these surroundings had 68 joules of work done to it. Okay, so the negative there is just to kind of show us where the work is going and where it's coming from. So the work was done by the system onto the surroundings, since it's a negative one. Okay, so if our piston had in fact lowered the volume, we would actually have the opposite sign, and we would end up having the system having work done to it and the surroundings doing the work. So, but that's just, again, same thing, sign things. Okay, so pressure volume work is happy for us. Okay, so more definitions. We have another term that we're going to talk about, which is going to be, what am I saying? Pressure times volume. Yeah. H is called the enthalpy, and that is a measure of thermal energy. And we're going to see enthalpy is going to be a very useful term for us in talking about how much energy is going to be associated with chemical reactions. And again, internal energy, pressure, volume, all that fun stuff. Just so we all know, all these guys are state functions. Remember, state functions do not matter what your pathway is. H, enthalpy, is also a state function. So it does not matter what, if our piston went up and down and up and down and up and down and finally went to its happy position, H is enthalpy. It would always have the same amount of energy associated with it. Alrighty, so let's see here. This is going to be a fun one for us. We often now talk about the change in enthalpy. Which is going to be represented by delta. And the change in enthalpy will therefore be the change of the internal energy and technically the change of pressure and volume, but most reactions occur at constant pressure. Because most things are taking place within, the atmosphere. We're not going out to space doing these, or doing them in like bombs or something. So since most reactions occur at constant pressure, we kind of omit a delta with P. So we just say pressure because it's not changing, typically. And so we can sub some other things in here. We remember that delta E is Q plus W, right? And if we remember that W is negative P delta V, we can sub these things in. Who doesn't love deriving equations? What's negative P delta V plus P delta V? They cancel out, right? So we're going to see that the change in thermal energy is going to be equal to the heat. Exciting stuff. One thing to note, though, this is often written Q sub P, which means Q at constant pressure. So again, the change in thermal energy or enthalpy, I should not put quotations, I meant parentheses, my bad, is just going to be equal to the constant or the heat at constant pressure. And so we're going to see that this is going to be a very valuable way for us to calculate things, because that's what we love to do, right? So this is how we're going to relate thermal energy to heat. So while they are not technically the same thing, the change in thermal energy is absolutely related to heat. So one thing that you guys haven't probably thought about that, so we'll just leave it alone. So I don't want to confuse you any more than I have to. Okay, cool. So what this means is we can do all sorts of fun calculations with it. If, for example, we can use this to predict how much heat energy is going to come out of a reaction. We know delta anything is always final minus initial. But in chemical reactions, it's the same thing as saying the enthalpy of the products minus the enthalpy of the reactants. And trust me, we are going somewhere with all this. So I know I'm just throwing out a whole bunch of equations at you, but we'll see how this is going to work. So we're able to, for example, figure out how much heat is going to be associated with a reaction by doing this. So here's a reaction that we've studied before. Combustion reaction. I have this written down somewhere. There it is. Okay. Oops. Let's take a look at this. So we're going to see that reactions will have an enthalpy associated with them, which tomorrow we will learn to calculate from just looking at a reaction using some standard information. But for now, I've given it to you. This is telling us that this, this reaction is associated with a change in internal thermal heat or thermal energy of negative 890 kilojoules. What that means for us, exciting, this means we can get a whole bunch of conversion factors out. Stop it. Feel like I'm writing exactly the same thing over and over. It's because I am. The delta H for your reaction, whatever it may be, can be used as a conversion factor. Ooh, notice these are all our reaction coefficients. And they're all equal to our delta H for the reaction. So this means we can now figure out how much heat we're going to get out of a reaction by putting in a certain amount of materials. So, boom, here we go. Let's say we have 10 grams of methane. Okay, how much heat is released by combustion of this methane. So, just like always, let me plan it first. And let's say in kilojoules, just so we have a unit for us. So we are starting with grams. We want to end up with kilojoules. Oh, and look, we have all these conversion factors that we've been able to get. And one of them in particular will give us moles of methane into kilojoules of energy. And so our plan is just going from grams to moles to kilojoules. This conversion factor will be our delta H. And what's the conversion factor from grams to moles again? I can't remember. How do we go from grams to moles? Shane, of course, has the number, but yeah, I was going for just molar mass. Or molar rate, molecular weight, whatever you want to do, yeah. But yes, the number would be 16.04. Yeah, for sure. So, that's our plan. Thank you for doing the number for me, so I guess that helps. So now let's go ahead and look up. Since the reaction coefficient for methane was 1, that tells us 1 mole of methane is equal to the delta H. So again, as always, units should cancel out. And thank God Kevin has done the work for us. And he said negative 555 kilojoules. Yeah, let's just go ahead and make the sig figs easy for us. I'm going to just throw some dots. Will be 3 sig figs now. Awesome. And we have agreement. That's even better. So no 554 and 556 this time. That's awesome. So this tells us, after doing all this stuff, this tells us combustion of 10 grams of methane produces 555 kilojoules of heat. So again, we're probably looking at that sign and saying, why am I just saying 555? We remember that the sign of Q, if it's negative, that means it's exothermic, right? It's giving away the heat. So typically when we say these things in words, we just say positive, but we understand from our calculation that the negative heat there meant it's being produced. It is a product of the reaction. It is going to go into the surroundings and heat something else up. And so this would be kind of like if we were to say in words what we just did, that is how we would do it. And now we can have even more fun, as you should always be scared of that. We can relate for us, the easiest way to think about, okay, absolutely. Perfect. So if we were to say we produced whatever amount of water. Okay, here, let's just do it. Goodbye Q to temperature. And so, yes, you would be exactly right in saying, just gonna throw this out real quick. Is boom, done. And you would be able to do that. So this is how you would set that up. It's the same plan. But very good, Tyler. You have noticed that, again, we have our reaction coefficient here. I didn't actually want to do this problem, but I guess since we've already done it out, let's just do the calculation, because why not? Thank you. You guys are the best. Okay, so if we were to produce that amount of water, we would also have produced 509 kilojoules of energy. So yeah, no, it's a very good idea just to show, remembering that delta H is related to your reaction coefficients. That will be very, very, very important for us tomorrow. So yeah, very good. Okay, let's relate this crap to temperature. So, bad news. For every different substance, unfortunately, a different amount or the same amount of heat would yield a different temperature change. So if you put 509 kilojoules of heat into different substances, they will reach different temperatures. Unfortunately, there's not a easy way. We're going to have to calculate it for every different substance by using a property known as the specific, I don't know why I did the therefore things. Specific heat capacity. Yes, Kevin has already memorized all of chemistry, so he's going to be teaching today, which is going to be, it's represented C, by the way. That's the molar mass of water. Molar mass of water, yeah. It's going to be the heat over the, typically it's mass, and it's for 1 gram to change 1 degree Celsius. So in words, the amount of heat required to increase the temperature of 1 gram of substance by 1 degree Celsius. And we're going to see C is different not only for every substance, but also for different states of matter. For example, the C for Oh my goodness. Okay. Star-Lord, you're getting ahead of yourself. Not quite. Because I haven't told you anything about a temperature change, we have not gotten into that yet. So, not quite. This would be, for example, the specific heat capacity for liquid water. We're going to see for ice, actually I would have to look this up. Let's see, specific heat capacity of ice. Apparently is, oh there it is, okay. 2.04 joules per gram degree Celsius. So they are, I know, right? Which is awesome. I'm very happy to see that. You will, of course, never have to memorize these numbers. These I'm just giving you as examples. We're going to see that different substances will have different heat capacities as well as different states of matter. I have actually in your texts around here. Aha! There, I think is going to be like a list of all these things around here. Okay, let's see. Let's give you, here's a couple. Okay, how about of aluminum? Solid. It's 0.90 joules per gram degrees Celsius. So just some examples. So these numbers can go all over the place. Aha, let's get to that, Shane. And one more. Boom. Okay, just some examples for what these numbers might look like. We see that a lower C means easier to change the temp. Yeah, I know, Shane. It's contagious. The curiosity is contagious. So, we're going to see that, for example, not for example, as a result, metals usually have low specific heat capacities, and things that are insulators and since we know metals conduct heat, right, they're going to absorb it rather easily, and so those typically will have a low specific heat, and things that are going to be more insulating will typically have higher heat capacities. And so you're going to see that, so it's not necessarily exactly the same thing, insulating versus heat capacity, but there's a trend there. Yeah, and so liquid water is actually got one of the highest ones we have. And so you're going to see that high specific heat things are very good to use as coolants, because they can actually hold quite a bit of energy within them to change their temperature. So, like in my lovely computer here, I'm using liquid cooling because the water in there is a much better kind of place to dump that heat into, because it can hold a lot of that heat before it changes temperature. And so it would be a pretty bad idea to use mercury as a coolant, because it would just heat up like that. And then, that would start burning things, and, not a good idea. Okay, so let's see how we can relate this. So if the units of C are joules per gram degree Celsius, we're going to see that for variables, that's what it's going to look like. So just from the units of the specific heat capacity, we can see kind of an equation that's going to come out of this. by plugging in quantities that we'll have for this. And guess what? Delta T will always be final minus initial. However, a lot of us like to put equations where we don't have fractions, so often you'll see this as MC delta T, which we could remember because, look, it's your MCAT. Ho, ho, ho. So for those of you who are going to medical school, this equation is the exam you're going to have to take to apply. So often I will just say MCAT just because it's a lot easier for me to say MCAT versus MC delta T or whatever, so I will refer to it that way. So we're going to see, for example, let's say sample of water is at 10 degrees. How much heat is required to bring water to this particular temperature? I will just tell you right now, so C for liquid water was 4.184 joules per gram degree Celsius. And so, again, this is a matter of identifying things from our equation. So M is going to be our mass. C is our constant here, our specific heat capacity. And then our delta T is going to be our final temperature to minus our initial temperature. Doing all this fun stuff. I'm sure Kevin's already done it, but I can do it too. Or let's see if Shane beats Kevin. Should have a competition. Let's see if I win. Oh-ho. Aha! I got Kevin with the sig figs. So we got this much. Aha, but look. All these things are going to need 3 sig figs, right? Ha ha ha. Yeah, I know. I use Google as my calculator usually. I just type stuff in, so. We need 3 sig figs on this one. So I finally got Kevin. Guess what? There's a part B. What was I going to say? Assume no heat lost to the surroundings. Very often, we are going to make the assumption that we're not going to lose heat, although in reality, of course, we will lose some heat. But just like in physics, we ignore air resistance, here we're going to assume that we do not lose any heat. So remember the delta H for methane combustion was how do we want to go about this problem? As always, guess what? It's just a unit conversion as every other problem in chemistry is. So, how much methane? That's a quantity, right? Let's say in grams, because I should always give you a unit. We're looking for grams of methane, right? We know that we had this. We had our amount of joules. And so, remembering always that we can never use grams as they are, we're going to see that we can go in between joules and or kilojoules and moles by using that delta H there. Exactly. Just like that, Tyler. Perfect. So, and in fact, we should not technically have rounded our 5602 joules, but whatever. We'll do it. Okay, so look, I'll keep our 3 sig figs there. Conversion between kilojoules and joules is right 10 to the 3. We have here our delta H. Oops, not delta. CH4. And since I asked for grams, we're going to have to use our molar mass. Remember, this is our unit conversion. And that's just metric, whatever. And so doing this, you can figure it out. While you do it, I'm going to just mess with the AC real quick. It's freezing. Okay. Do we have an answer? Not yet. Why has nobody done this one yet? I have to do it myself? That's not fair. Okay, I'm going to leave my unrounded answer. Oops, divided by 890. 16. 4. Oh, how interesting. I got a small number. Okay, so remember that technically this was this should be a negative joules, since remember this is heat that's going to be so this is an interesting point. So this was heat that we needed to put into the system, right? If we have to that we're putting into the system, right? So how did 816? How did you guys get such big numbers? I got 0.101 grams. Okay, apparently we have to do this. Oops, we've disconnected too. Even the computer has gotten a different answer. 14? This is just a calculation. How did we all get such different answers? I like yours the most. And I think mine was slightly off from that. 90. My calculation looks like I put everything in Google correctly. Okay, cool. I know, calculators suck. So this is what I got. Yeah. Okay, good. We have at least a couple people who got it. Yeah. So just understanding this is the energy that we have to give off. Tyler, double check. There's no way it should be 14K. Make sure you're dividing properly also. Because if we're thinking about it, we have a number in the thousands that we're dividing by 1,000 and then dividing by almost another 1,000. So it's should be a small number. Okay, awesome. So Shane, you apparently had 14K also. So what was the problem there? Did you like put something in the numerator instead of denominator or something, or what's going on? Yeah. So why should the negative matter? The negative just changes the sign. The problem is on your calculator, it might see it as a minus instead of a negative. So it might be subtracting instead of dividing. So yeah, so point 101 is correct, Melissa. You are okay. So that negative is there because of this dude. That's why we had a negative, but we forgot to put a negative with our joules at the beginning. So that was my fault for forgetting to put that there. So remembering, well, I mean, one way to think about it, your mass has to be positive, right? So we can just forget about the negative signs. But that's one way to do it. But yeah, this was my fault for forgetting that negative because we have to. This energy is being released by the reaction, right? So it's all about systems and surroundings and all that stuff. So again, what's important here? Masses cannot be negative, so that's why we're seeing it that way. Okay, since remember we're looking at a negative energy because that's how much energy is being released. Yeah, I know. This stuff gets exciting. Okay. One more thing for you guys for today. Awesome. Perfect. So it looks like everybody's got the point 101 now, which is great. So, fun last equation for the day. The amount of heat lost by something is the opposite of the heat gained by the other thing. So whichever one's systems and surroundings, it's just the opposite. Whatever heat you've lost is negative of the heat you've gained. Nothing crazy there. Again, it's all about where heat is going. So with that, typically this is often written is the heat in the solution is negative of the heat of your reaction. And so that's where that negative should have come from. So typically, because most reactions are in solution, and so the solution is therefore these surroundings. So the reaction will be your system, and typically the solution around it is going to be your surroundings. And so we can see what this means by now combining all this fun stuff together. So let's take 50 mils of... Actually, I think the book had a good problem for this. Let me just look that up real quick. About combining solutions here. Let's see. Where was it? I liked seeing it this morning. Hess's law. Aha! Okay, cool. Yes. Oops. So we're going to combine our solution chemistry now. Okay, and then blah, blah, blah. Okay, so we also have some temperatures. 227.5 degrees Celsius. And let's see. Anything else on this? Yeah, okay, cool. Just write out all this crap. And then what other assumption were we going to make? No heat loss. And that those are our assumptions. Yes, I can. Now that I've closed it. In the meantime, where did I find this problem? For me, it is on page 184. But I'm using the 13th edition, so it may be like slightly different. But this is exercise 5.7 in our textbook, which is 15 equations. Yes, that one I can't. We can do that at the end today. But let's look at this problem. We're probably going to run over a little bit in time again, just because I want to make sure that we can understand exactly what's happening here. So, a few more things. For water, that's our specific heat capacity. There we go. Okay, fun. What the heck is this going to mean? So, let's look through this here. Is there anything that we can go through right away? Right? So, we have a bunch of numbers here. Probably first thing we should do is write a chemical equation. That's usually something good to do, right? All right, it's already balanced. I guess that's easy. So if you're ever confused on a problem, just start by writing an equation. That will always be useful in some way or another. So if we look at this, we have a whole bunch of things for us. We know we're going to probably want to do something with Q, right? Because we're trying to figure out delta H, right? And remembering Q is the same thing as delta H for 1 mole, right? But let's erase that. We also know Q is our MCAT formula. We have a C already given to us in the problem. However, we don't quite have a mass, and we do have a delta T. We can figure out the delta T. So what we're supposed to be looking at here is remembering that the Q of the solution is the negative Q of the reaction, right? That is the thing that I told us right beforehand. And so this solution, it's telling us that we have 100 ml of solution, and we have its density is 1 grams per mil. So that means our solution is actually going to be 100 grams. Just using the density as a conversion factor, 100 times 1. Here, I'll throw in another sig fig, just to make us all happy. So that's going to be the M we use. So we're finding out the heat for the solution because that will also tell us the heat for the reaction. C is given to us. And delta T, it looks like we have 27.5 minus 21. Shane, I have a special assignment for you. Convert both of those temperatures to Kelvin for me. Okay, just Shane. Everybody else will continue doing the problem. So, let's do our math. Okay. Doing that, what I got was 2719.6 joules. And it looks like with this we're probably going to need 2 sig figs. Why 2, you ask? Because... Did I mess something up, Kevin? Oh, okay, cool. Okay. Remember that this is 6.5 degrees. Thank you, Shane. And with that, can you also convert 6.5 degrees to Kelvin? That will be for later. So I just want to show you guys something. Okay, so understanding that this was the Q of our solution, right? The Q for our reaction must be the negative of that. And so, since we now have a Q, we can relate that to delta H by using, thank you, Shane. So we'll get to those in a second. So, remembering our reaction, we have some amounts, right? Now we can finally bring in our stoichiometry goodness. So overall, these two are the same, right? The 50 mils and 1 molar of each solution. It doesn't matter which one we use because they're identical. But technically, if they weren't, we might have to do a limiting reactant type problem. Yikes. But for now, they're the same, so we're happy. So we can figure out how many moles are taking are participating in this reaction. So remembering molarity is our conversion from moles to liters. That tells us we can find out how many moles are taking place in this reaction. And so that's going to be, if I could do simple math, oh my gosh, 500 moles of HCl, or NaOH, doesn't matter. They're the same thing. So this is telling us this many moles of HCl. Yeah, this should explode your brain. This is telling us that we got negative 2719.6 joules out of this thing. By reacting that many moles of HCl or NaOH, does not matter, we got out that much energy. And so, remembering that we have a conversion factor for moles to kilojoules, right? And that is where our delta H is going to come from. And so, we know that delta H should be some amount of joules per 1 mole HCl. I know your brains are exploding. Welcome to thermochemistry. Don't worry. It gets better. In a bad way. Okay, anyways, so we're going to be able to see that's going to be our joules over our moles. Yeah, we all need a nap. Doing all this fun stuff. Yeah. So, Shane, you are absolutely right. However, the delta H is usually given for the reaction in terms of its coefficients. So the delta H associated with 0.05 moles of HCl is equal to that many joules, for sure. But what we're looking for here, typically delta H is given for 1 mole, or whatever the coefficient may be. So we are just expanding our 0.05 moles into 1 mole. I'll explain. Let me just do the math real quick. 2719.6 divided by 0.5. Okay, and that's negative 54,392 joules per mole of HCl. And if we just make this real nice with our sig figs and make things nice and easy for us, typically, again, we're using delta H's as that much. It is absolutely correct what you've said, that delta H is equal to Q. For sure. But delta H for a reaction is uses the coefficients. So that Q was associated with 0.05 moles. We need to basically just find the Q for 1 mole. And that would be our delta H for the reaction. So, our brains have officially exploded. We have done a crap ton of work for this problem. Yikes. But this is essentially combining all of the stuff we've learned today, all at once, along with some of the stuff that we've learned last in like solution chemistry and all that fun stuff. So, yeah, I guess I had left off that distinction that delta H for a reaction. Uh-oh, Tyler, I made it kilojoules. So that's why. If I wanted, I could have left it as 54,000 joules. Either way, Tyler, same thing. I just put it in kilojoules just because I like to have the small numbers, and usually delta H's are kilojoules. Is this reaction exo or endothermic? Exo, yes. Negative delta H. And so that's why it heated up the surroundings, it heated up the solution, and that's why the solution's temperature increased. So I realize A lot of your brains are overloaded with this problem. Totally, I don't want to say normal. I don't want to say unavoidable also, but given time constraints and all that stuff, and COVID being the disaster that it is, I understand. This is tough. This is a tough problem. Yes, and it's also fairly well known that neutralization reactions are exothermic. So again, we have not kind of violated any things that we've learned already. So yeah, and so that's why heat is a product. That's why it's negative here. Okay, Shane, last thing. If we had converted our temperatures to Kelvin, if we do that, I guess that would be 6.50 Kelvin. And so notice that before our delta T, that was is also 6.5 Celsius. So this is why, Shane, it does not matter if you use Kelvin or Celsius. Totally okay, because we're subtracting them. One thing that we do not ever want to do, yeah, they're the same size. 1 Kelvin and 1 degree Celsius are the same magnitude as each other. However, our delta T is not 279.65 Kelvin. Because this is a change in temperature, a change in Kelvin is the same as a change in Celsius. So sometimes you'll see specific heats given with Kelvin instead. Doesn't matter. Use either one, Celsius or Kelvin. They're exactly the same because it's a change in temperature. Okay, so just to address that, so you may see these things, but you don't have to actually convert them to Kelvin. So save your time, just use them as Celsius. No problems there. Okay, sorry for running late. I understand we've done a lot of stuff today. Tomorrow we'll have more, and we will probably finish thermochemistry on Monday. I don't think we'll get through all of it tomorrow. Oh, yes, sure. There you go. If you want the main equations for this, here they are. And let me just make that distinction. Delta H for a reaction. Just 5, I know. So, well, technically 6. So just making the distinction that delta H for a reaction, you have to relate it to the reaction coefficients. So just the delta H, the change in thermal energy for that quantity is QP, but for a reaction, you do it for whatever the coefficient is for the moles. Okay, so that's all of you right now. Thermochem is tough. I understand it. Or rather, I understand that it is tough. I mean, I guess I also understand thermochemistry, but I understand this is a tough subject. Yeah, right. Oh well. Yes, Tyler. What about it? Yes, correct. Right, and just you can just multiply the negative on either side, right? If you multiply both sides of that equation by -1, you'll get the opposite one. So, yeah, it can definitely go either way. I mean, we could also say negative work is P delta V. Yeah, yeah, yeah. So, I'm not changing it. It's still there's still the opposite. Multiply both sides of that reaction by -1, and you'll get the other one that I wrote before. That's just me forgetting which one I wrote. It doesn't really matter which one has the negative as long as they're the opposite. So, cool. Rest your brains. Um, I still haven't decided about homework yet because the homework that I had in mind you will not be able to do yet. So, we'll see. Maybe for this week I'll just give you a few problems uh, like this and just have you work on those because I know they're going to take a lot of time. So maybe that's what we'll do, and we'll save the other delta H stuff for next week. Okay, yeah, we'll do that. And Saturday and Sunday, let's just have continuous thermochem. No, I will not ever do a Friday. So yeah, I will definitely show mercy. That's why I'm not going to give you a crap ton of homework right away. So I understand this is tough. So with that, go take a nap or a drink, whatever will help you to relax a bit. So okay, yeah, gym time. There you go. Yeah, beer 30, right? Yeah, beer 30. It's pretty close. So okay, take care, everyone. I will see you guys tomorrow, and we'll continue this exciting topic.